So in this screencast we'll go through the different instruction formats in the Hack computer. And first off we'll look at the A instruction. So this is used to set the A register to a particular 15-bit value. So the register itself is 16 bits, but bit 15 is used to signify which type of instruction it is. For an A instruction, this bit will be a 0, and then the 15 remaining bits will just contain the ones and zeros that form the binary value. So for example, this @15 command will load the binary value 15 into the A register. But just note with the syntax, and it's not using assignment, so this is an invalid command. We need to use this syntax to load that value into the A register. So for example, where we've got @15, the instruction, well, we know 15 in binary is just 1, 1, 1, 1, and the rest zeros. So all these bits here will be 0, plus this final 0 in the bit 15 to signify that it's an instruction. So the instruction is very easy to assemble. You just simply convert the value in the instruction into its binary equivalent. So the C instruction, this is a kind of compute instruction of the Hack computer, and it's the kind of workhorse of your program, if you will. So it's made up of a destination where we store the result of the operation, the actual computation we want to carry out, and then any jump condition that's required. So there's actually 3 possible forms of this instruction. So see, each one of them contains a computation, so we always have to do a computation. So the ALU is always going to do something, but we can see that the destination and jump fields are optional. So it gives us these different forms of instruction, but they're all made up of some destination, a computation, and a jump. So the actual format for this instruction, now bit 15, this is now a 1. So when we see bit 15 as a 1, we know that's a C instruction. 14 and 13 are not used, so they're just set to 1. And then the A bit is used to select between A and M. So for some of the operations, we'll do the operation on A, one of the inputs will be A, and for different operations, one of the inputs will be M, and whether it's A or M depends on the A bit. The actual computation done by the ALU is specified by the 6 C bits. And we've got the 3 destination bits, so this sets a destination that appears in the instruction, which is a combination of A, D and M. And then we've also got the 3 jump bits. So this is where we're looking whether something is greater than 0, less than 0, or equal to 0. That specifies any jump that's part of the instruction. So the computation bits, very simple. These are just these 6 bits of the ALU. There's 28 different instructions, and the instruction set are represented by 28 different combinations of these bits. And they're shown in this table here. So we can see here we've got the A, where the A is 0 and A is M. And that basically says whether we're going to do an A or an M in the instruction. And so on. So just depending on which of these instructions we want to do. So for example, if we was doing D plus M, this would be this value of the 6 C bits, and then A will be equal to 1. For the destination, to assemble that again is very easy. We just look which mnemonic is used. If there's no destination specified, these 3 bits will just be all zeros. And then essentially D3 controls M, D2 controls D, D1 controls A, and they can obviously be a combination of those. So we just look at the mnemonic. So if we see the destination is AMD, the 3 destination bits will be 1, 1, 1. The jump bits these tell the CPU what to do next. So typically it's just going to be fetching the next instruction in the ROM. As it executes the code, it'll go instruction 1, 2, 3, 4, 5, 6, and so on. But then if certain conditions are met, we might need to do a jump condition, which is that'll be specified in the C instruction. So if the jump is going to occur, then we're just going to load the program counter with a new value. So we might do 5, 6, 7, 8, 15, 16, 17. We'll jump to 15. So the actual value you want to jump to, the address, is always the current value that's stored in the A register. So before a C instruction for jump specified, there always needs to be an A instruction first, which sets the value of A, which is an instruction to jump to. And then whether the jump occurs or not actually depends on the output of the CPU. So we look at the flags, whether it's 0 or negative. And if it meets a particular jump condition, then the jump will occur and the value in A will be loaded into the program counter. So the jumps are specified in this table. So again, it's just when we're assembling, it's very simple. We just look at which mnemonic appears. So for example, if we see the jump condition is jump not equal to, we know that those 3 bits will be equal to 1, 0, 1.